Aloha! Many textbooks explain the central limit theorem in this way. When we take sufficiently large random samples, such as 30 or above, from any population, the distribution of the sample statistics will tend to follow a normal distribution, regardless of the population's original distribution. Many people viewed 30 as a magical number. Some researchers argued that if the sample size is less than 30 and the population is not normal, the sampling distribution will be a t-distribution, otherwise a normal distribution. This is nothing more than an urban legend. Paul Velleman, the inventor of Data Desk, traced this misconception back to the pre-computer age. When high-power computers were not available, statisticians had to use a t-table only. The t-family goes on and on for any number of degrees of freedom, and t-distribution is really normal if and only if the degree of freedom is infinite. However, it was not practical to have such a long t-table. As a result, a compromise was made at around 30 degrees of freedom because it could fit nicely in one page. In an article entitled, "Why is n equals to 30 magic?" and other frequently asked questions, Miller reminded us that 30 is not a magical number for switching from t to z in inference about a mean. Indeed, the distinction between t and z procedures for a mean has nothing to do with sample size. In a similar vein, statistician Tim Hesterberg argued that the traditional rule of using z's or t-tests for sample sizes of 30 or more is outdated and should be replaced with bootstrap-based methods. He emphasizes that achieving highly accurate results may require a large number of bootstrap samples, potentially up to 64,000, far exceeding traditional guidelines. As a result, Hesterberg advocates for a shift in statistics education to prioritize teaching bootstrap diagnostics over relying on outdated rules. The number 30 has been widely accepted in statistical education and practice as a reasonable rule of thumb. Because it works well for some applications, it has been passed down through textbooks and became a convention. However, this doesn't mean that 30 is a strict cutoff. For populations with extreme skewness or high variability, alternate modeling methods might be necessary. In the era of big data, a sample size of 30 is considered very small and may lead to unreliable inferences, especially when data are complex or has high variability. The idea of 30 as a sufficient cutoff is somewhat outdated in modern applications where large data sets are available. With the vast data sets now available, we often encounter high-dimensional, complex, or highly skewed data. In these cases, larger sample sizes are necessary to capture the data's variability and ensure reliable estimates. Modern data sources, such as online behavioral data, transaction data, or sensor data, can have nuances that a sample of 30 would likely miss. The 30 is enough rule served its purpose when sample data was often scarce, but in today's data-rich environment, it's better to focus on sample adequacy based on context and distribution characteristics, not just an arbitrary number. Thank you for watching this video. I hope from now on you will move away from using any fixed cutoff for decision-making. Data analysis is contextual and complex. Mahalo!